A distribution switch loses a link in the middle of the workday. Users do not care that Layer 2 has a loop prevention protocol. They care that file shares freeze, calls glitch, and the help desk lights up. Classic STP can make them wait close to 50 seconds while timers expire and ports crawl through states. Rapid Spanning Tree Protocol exists for that exact moment. Same loop-free goal, same basic election logic, but a faster reaction when the topology changes. Start with the version names, because Cisco output can make this feel more confusing than it is. The original standard STP is IEEE 802.1d. Cisco's per VLAN version is PVST+, which builds a separate spanning tree for each VLAN. Rapid STP is IEEE 802.1w. Cisco's version is Rapid PVST+, which gives each VLAN its own rapid spanning tree. On a Cisco switch, spanning tree mode Rapid PVST enables it, but Show Spanning Tree reports the protocol as RSTP. If the output says I take a plea, you are looking at PVST+, not Rapid PVST+. The first practical decision is scale. Per VLAN spanning tree is useful because different VLANs can prefer different routes and links. But 100 VLANs can also mean 100 STP instances and 100 sets of BPDUs every 2 seconds. If the design really only needs a few traffic patterns, multiple spanning tree can group many VLANs into a smaller number of instances while still using rapid mechanics. For CCNA, remember the trade-off. PVST+ and Rapid PVST+ are per VLAN. MST groups VLANs into instances. Now imagine 2 redundant switches deciding which links stay active. RSTP does not reinvent the election algorithm. The root bridge is still the lowest bridge ID. Each non-root switch still chooses one root port by lowest root cost, then lowest neighbor bridge ID, then lowest neighbor port ID. Each segment still gets one designated port, chosen by lowest root cost and then lowest bridge ID. If a tie happens between local ports on the same switch, the lowest local port ID wins. The topology math is familiar. The speed comes from what happens after the decision. Port cost is one place where RSTP modernizes the numbers. Original STP short costs were built around older speeds. 10 megabits is 100, 100 megabits is 19, 1 gigabit is 4, and 10 gigabits is 2. RSTP introduced long costs for faster links. 10 megabits is 2 million, 100 megabits is 200,000, 1 gigabit is 20,000, 10 gigabits is 2,000, 100 gigabits is 200, 1 terabit is 20, and 10 terabits is 2. Anchor on 10 gigabits equals 2,000, then move by powers of 10. Do not assume a switch uses long costs just because it runs Rapid PVST+. The cost method depends on platform and software. Show Spanning Tree Path Cost method tells you whether the switch is using short or long. Spanning Tree Path Cost method, short, or Spanning Tree Path Cost method, long, changes it. The exam angle is simple. Know both cost families, and know the command that reveals which one is active. Next, port states. Classic STP talks about blocking, listening, learning, and forwarding. RSTP simplifies that into discarding, learning, and forwarding. Discarding covers the old blocking and listening behavior. The port is not forwarding user traffic. If the port becomes a root port or designated port, and the rapid sync succeeds, it can jump straight to forwarding. If sync fails, it takes the slow path. 15 seconds in discarding, 15 seconds in learning, then forwarding. That sync behavior is why RSTP feels rapid. Switches actively coordinate instead of waiting for old timers. But the neighbor has to participate. If an RSTP switch connects to an old STP switch, a router, or a host without the right edge configuration, the rapid handshake cannot do its magic. RSTP and STP are compatible, but compatibility does not mean fast. Compatibility means the port can fall back and behave like classic STP. Port roles are the next exam trap. Root ports and designated ports keep the same meaning. A root port points toward the root bridge, and forwards. A designated port is the forwarding port for a segment and points away from the root. Classic STP called every other port non-designated. RSTP splits that idea into alternate and backup, and the difference tells you what kind of standby path the port represents. An alternate port is the useful one you will actually see. It is a backup path toward the root bridge. If the current root port fails, the alternate can become the new forwarding path quickly. A simple mental model: an alternate port is discarding, and it is connected to a designated port on another switch. The switch is not the designated bridge for that segment, so it keeps the port blocked until it is needed. A backup port is much rarer. It backs up a designated port on the same switch, on the same shared segment. That usually means an old hub or some unusual shared medium. If two ports on one switch connect to the same collision domain, one can be designated and the other can be backup. You probably will not build that design, but the exam may still ask. Alternate is another path to the root through another switch. Backup is another path to the same segment on the same switch. Now return to the outage story. In classic STP, a switch can wait 20 seconds for the max age timer after BPDUs stop arriving, then spend more time moving through listening and learning. That is where the 50-second number comes from. In RSTP, a switch reacts after missing 3 BPDUs. With the default 2-second hello timer, that is about 6 seconds. If the link physically goes down, the reaction can be even faster because the switch does not need to wait for missed BPDUs. RSTP also changes BPDU behavior. In classic STP, the root bridge originates BPDUs, and other switches relay them out designated ports. In RSTP, every switch sends BPDUs out its designated ports every 2 seconds, even if it has not just received one from the root. That local BPDU generation helps neighbors detect changes faster. For troubleshooting, it means RSTP is more conversational. Switches keep telling each other what they know. Link type decides whether a port can take the fast road. A point-to-point link is full duplex, normally switch-to-switch, and can use the RSTP sync mechanism for rapid forwarding. A shared link is half duplex, usually because a hub is involved, and cannot use rapid sync. It behaves like the slow, classic STP transition. An edge link connects to an end host, not another switch, and can immediately forward when configured with PortFast. Cisco handles those link types in a specific way. Full duplex links are treated as point-to-point automatically. Half duplex links are treated as shared automatically. You can manually set point-to-point or shared with spanning tree link type under the interface. Edge is different. You do not configure edge with spanning tree link type. You configure PortFast with spanning tree PortFast. In Show Spanning Tree Output, you may see P2P, RFIA, or P2P Edge depending on duplex and PortFast. Edge ports also affect topology change logic. A host plugging into a desk port should not make the whole Layer 2 domain flush and react like a switch-to-switch topology change. RSTP only triggers a topology change when a non-edge port moves to forwarding. Edge ports do not trigger topology changes when they come up, and ports moving to discarding do not trigger them either. That is why access ports should use PortFast when they really connect to end hosts. The guard features are the safety rails around all of this. Root guard protects the place where you know the root bridge should not appear. Picture a provider network connecting to a customer switch. If the customer switch sends a superior BPDU with a lower bridge ID, it could try to become root and drag the topology in the wrong direction. Root guard blocks that port into root inconsistent state instead. When the superior BPDUs stop, the port recovers. Configure it with spanning tree guard root. This loop guard protects a different failure. The danger is not a superior BPDU. The danger is silence. Suppose an alternate port should be discarding because it receives BPDUs from the designated side, but a software problem stops those BPDUs from arriving. Without protection, the switch might decide the path is safe and move the port to forwarding, creating a layer 2 loop. Loop guard keeps the port blocked in loop inconsistent state when expected BPDUs disappear. Configure it with spanning tree guard loop. Root guard and loop guard are mutually exclusive on the same port because they defend against opposite symptoms. Root guard reacts when a port receives a better BPDU than it should. Loop guard reacts when a port stops receiving BPDUs it should receive. If you remember superior versus missing, the feature names become logical instead of memorized. BPDU filter is the risky tool. It prevents BPDUs from being sent or received. On one interface, spanning tree BPDU filter enable makes the port ignore BPDUs and stop sending them, effectively disabling STP on that port. If that port ever connects to a switch, you may have just invited a loop. The global command, spanning tree PortFast BPDU filter default, is safer for PortFast ports. It suppresses BPDUs at first, but if a BPDU is received, PortFast and BPDU filter are disabled, and the port behaves normally again. For the exam, treat BPDU filter as a feature, with few good use cases. BPDU guard is usually the cleaner access port protection from the previous chapter. Root guard protects root placement. Loop guard protects against missing BPDUs on non-designated style paths. BPDU filter hides BPDUs, and hiding the thing STP uses to prevent loops should make you cautious. Here is the fast review. STP is 802.1d. RSTP is 802.1w. PVST Plus and Rapid PVST Plus are Cisco per VLAN versions. MST groups VLANs into fewer instances. RSTP uses the same route and port selection logic as STP, but reacts faster through synchronization and local BPDU generation. Remember the 3 states: discarding, learning, forwarding. Remember the 4 roles: root, designated; alternate, backup. Alternate is a standby path toward the root. Backup is a standby path to the same shared segment on the same switch. Remember the 3 link types: point-to-point for full duplex rapid sync, shared for half duplex slow behavior, and edge for PortFast host ports. And remember the decision story. When the network changes, do not just ask which port forwards. Ask why it is safe to forward, how quickly it can forward, and what guard prevents the wrong device or missing BPDU from breaking the design. That is RSTP in practice. Same loop-free tree, faster recovery, and better controls around the edges.